All right, let's go ahead and get started. Sorry for the delay. I'm going to try something a little bit new. I'm going to just see how it works out to record the lecture. I'm a little concerned that actually the sound won't work out. I was trying to use my wireless microphone, but the levels aren't high enough for it to connect to the computer. So I've got this webcam microphone going, but I don't know if it's going to be able to reach me everywhere in the room. Everybody get a copy of the notes? Is this your copy of the notes you've already done? No. I think we've been through this a couple times before already, that on Monday there's no class because of a holiday. Wednesday and Friday, class will be posted online, so you can watch those videos before our quiz on Monday, so you can know whatever magical keyword I want you to know for the quiz there. Also on Monday, the coverage may come from homework 1, which is due on Friday the 25th. So that's 7 days from today. Slide it under my office door before they lock the doors in the evening. And we're going to go over an example today that should give you a pretty good start on this assignment. There are a few things maybe you've already managed to work on so far. So any questions on the announcements? Okay, this is where we left off last time. We weren't able to get to the shear velocity slide. It was in last lecture's notes. Shear velocity comes from combining two ideas. On the left, this expression for head loss due to pipe friction is what we got when we were considering resistance to flow due to shear stress. And so this was the relationship between the shear stress, which is essentially the level of interaction between the surface and the fluid that's flowing over, the shear stress. The length was whatever distance that we're considering the 2 points, flow between 2 points. The length was whatever characteristic distance that is, hydraulic radius, and the unit weight of the fluid, gamma. Okay, so that was one idea for how to develop friction due to head loss due to friction. This other expression, this is the Darcy-Weisbach friction factor. Its origin was when we considered how we can visualize energy loss as flow goes through a fluid. Remember, hydraulic grade lines, which we can see with a piezometer. If we consider the amount of energy loss in the hydraulic grade line, what we ultimately find out is that it's proportional to this friction factor F. And we haven't yet even gotten to the numerical gymnastics required to calculate F. But what we knew is that the head loss is proportional to F and also takes into account the length of the flow conduit, the velocity of the fluid, the diameter of the conduit, and so on. So if we combine these two ideas together by equating the H sub F term, then this is what we end up with. And screen seems to be locked up, probably because I'm recording. It's, I guess, resource intensive to do that. Let's see if we can do anything about it. Got a lot going on. Come on, you can do it. So much stuff running in the background on this machine. Well, all right, I guess my experiment has failed. I won't be recording these lectures.
That happens occasionally to even the other professors.
Oh, maybe it's because of this. It was Java. Curse you, Java. Yeah, that's the program that every time I reboot my computer, Java has a new update they want me to install. They are literally rewriting their software more often than I reboot my computer. All right. So if we relate these two ways of considering head loss due to pipe friction, the expression shear stress divided by density. We'll take a look at the units of shear stress divided by density. So the units are newtons per square meter. Those are the units of shear stress. And density is kilograms per cubic meter. So I've moved the kilograms down here to the denominator, cubic meter to the numerator. So we combine all those terms. We get the definition for a newton, then a kilogram meter per second squared. So this is the newton. Combining like terms, canceling things out, we end up with the units of shear stress divided by density is meter squared divided by second squared. And we're going to call shear stress divided by density the shear velocity squared. So that if we find the shear velocity itself, then that's the square root of shear stress divided by density. So why all the fuss? The reason why is that once we have shear velocity, we're going to be able to use it in calculating the thickness of the boundary layer. It's one of the input terms in a couple of criteria that tell you how thick the laminar cushion is at the edges of the pipe. And how thick that laminar cushion is partially determines what sort of energy losses there are due to pipe friction. So that's the direction we're heading today, is exploring this relationship between shear stress leading into the shear velocity and friction factor F. And this is an equation boxed for the same hinting reason that I boxed an equation previously. This is one that you'll need to use in the homework. Okay, so before we get there, I just want to introduce, so it's in the back of your mind, starting to sink in, the idea of a trapezoidal channel. So let's just take a look at some geometry before we jump back into the shear stress and shear velocity. In a trapezoidal channel, the variables that are commonly used is a lowercase b for the bottom width. Y is the depth of an open channel flow. These sides have a slope to them, and that's pretty common for trapezoidal channels to have side slope rather than just being strictly rectangular, because oftentimes the sides are made out of materials that can't have a vertical face to it. Sand, you couldn't dig a vertical face to a sand channel, but you could have a trapezoidal channel potentially. So sometimes the side slope will be given in terms of t. They'll say, t equals 2. So if t was 2, what that means is that the trapezoidal channel has a side slope where each unit of horizontal length is double each vertical unit of length. So it would be essentially a 2-to-1 horizontal to vertical side slope if t equals 2. So just to let you know what t is. So the same flow resistance, flow rate relationships that apply in pipes also apply in open channel flow. We did that force balance on the fluid element looking at a pipe last time, and that same force balance applies if it's an element of water that's flying through a channel. So all of these relationships are still valid. So let's consider what's the hydraulic radius for a trapezoidal channel in terms of B and Y. Remember, in an open channel, in a pipe that's full, hydraulic radius is easy. It's just the diameter divided by 4. But a trapezoidal channel, number one, doesn't have a diameter, and it's not flowing full. So we can't use this simplification to find what's the hydraulic radius in terms of B and Y. Okay, an area of the trapezoidal channel. Okay, we've got these side slopes here. Okay, so here's some water, and we want to know the area. The area, if you break it up into segments, okay, if we break it up into segments, we've got B and Y. And so the area will be B times Y. That gives us that area. And then what's the area of this side triangle? It's also going to depend on the side slope, T. Now, this, for something that has a side slope of 1 to T, then the length of this is going to be the square root of y squared plus ty squared. So that's the length of that side as a function of the depth of the water and the side slope that's known. So then the area is by plus the effect of the side triangles here. It's y t times y. And the wetted perimeter, so the wetted perimeter is this distance where the water is touching the surface. That is b, the bottom width, plus 2 times y squared plus ty squared. So the hydraulic radius is just the ratio of those two things. It's the area divided by the wetted perimeter. So by plus ty squared, b plus 2y square root of 1 plus t squared. How many of you have your books with you right now? Has anybody got a copy I can take a look at real quick? Since these are custom printed, I'm not sure if the page numbers line up the same as the original version. Page 301, yeah, good. They have the original page numbers, which is useful. On page 301 is a table of lots of formulas for area, wetted perimeter, hydraulic radius, and so on. So this is a very, very useful table for you to refer to for channel geometry. Page 301 is where that's at. So we'll get into a lot of open channel geometry a little bit later. But remember that in closed pipe flow, where the water is pressurized through the conduit, the energy grade line slope and the slope of the pipe are independent of one another. But in open channel flow, where the water is in contact with the atmosphere, then the slope of the energy grade line and the water surface slope and the channel slope are all equal to each other, as long as conditions are steady and uniform. Later in the semester, we're going to talk about when conditions aren't steady and uniform, and then those slopes aren't equal to each other. But they're equal as long as it's steady, uniform flow, meaning that the conditions of depth aren't changing with respect to position or with respect to time. Okay. Well, the Chezy equation is a way of, it's an empirical method of quantifying the effect of boundary roughness. It was one of the first methods that was proposed for characterizing how much energy loss there is in a channel due to pipe friction. And the roughness coefficient has units of length to the 1/2 power divided by time. In other words, it's a dimensionally non-homogeneous equation because the square root of hydraulic radius times the slope of the energy grade line wouldn't naturally give you velocity. But if you then multiply it by this roughness coefficient, then it will give you velocity, as long as you assume the roughness coefficient has these units of length to the 1/2 divided by time. It's been improved on since it was proposed. The Manning's equation, which we'll use a lot more this semester than the Chezy equation, has better results. And so really the only reason you do a homework problem using the Chezy equation is just to get a feel for one very simple method for estimating the effect of energy loss. So regarding the effect of boundary roughness and energy losses, we've talked about how in a pipe that the velocity distribution changes depending on if flow is laminar or turbulent. And if the flow is laminar, then we have a parabolic velocity distribution, meaning that there's a nice gradual transition between the velocity at the walls of the pipe, which is 0, Because of the no-slip condition, the water that's immediately touching the pipe walls, those molecules that are right in contact with the physical surface of the pipe are at the same velocity of the pipe, which is to say 0. But the further away you get from that surface, there's less influence because of the shear stress of any interaction, and so the velocity increases. With a logarithmic distribution, because of turbulent flow, there's a lot more variation in just random variation in velocity across the pipe cross-section, and so this flat surface here, it's not uniformly all particles have the same velocity. This is representing the average velocity. There may be some little pockets of water that have a much lower velocity, even though it's in the center of the pipe. There might be some sort of an eddy or a current inside of a channel that is less than the average. There might be some locations that are higher than the average. It's kind of a little bit random. But the point is that whether it's fully turbulent flow in a pipe where on average the velocity in the center of the pipe is quite high, regardless of whether it's laminar conditions generally or turbulent conditions generally in the pipe, there are these zones close to the pipe wall that have laminar flow. And so we're going to look at why that is for the rest of class today. This is a diagram that shows the further away you get from a pipe wall. So here is a pipe wall, and then as we go that direction, we're getting further away from the pipe into the fluid. So this y-axis is distance away from a pipe surface, or it could even be open channel, because the relationship is the same. The further away you get from a surface that's imparting resistance to a fluid as it moves. So if conditions are turbulent, then we have this profile of shear stress where there is shear stress far into the fluid. And the fluid is moving fast. That means that there's going to be resistance further away from the boundary than if the fluid is moving slowly. It's a low velocity, and conditions generally in the pipe are laminar. Then the reason why this dashed line isn't as high up on the y of it is that means that the shear stress isn't as big as you get further away from the pipe wall. So it looks like at this intercept, that's the point at where there's no more shear stress being felt by the fluid from its contact to the pipe. And so beyond here, it's flowing as though there's no pipe there at all. But when conditions are turbulent, then you can see the influence of that resistance extends more deeply into the fluid. Does that relationship make sense to everyone? Okay. The thickness of the boundary layer is variable. How much this cushion of laminar fluid, how thick it is, and how far it extends into the fluid is a function of the velocity of the fluid and what conditions are inside of the conduit or in the channel. So the thickness of this laminar sublayer depends on the Reynolds number, the roughness of the boundary itself. So for example, if the flow is moving fast, then that means that that boundary layer is going to be small. And so the location of this line is independent of this curve. They're plotted on the same graph just because they both exist in the pipe at the same time. But actually, if you have this shear stress, the big shear stress, then you'll have a small boundary layer. And if you have the laminar shear stress, then you'll have a big boundary layer. And so they're sort of inverse to one another. Water moves fast, that means there's lots of turbulence and lots of shear stress. If water moves fast, it means small laminar boundary layer. That cushion of conditions where the flow is laminar is very small. It's just a very tiny fraction of the conduit. But if the velocity is moving slowly, then we have a big laminar sublayer, and the shear stress profile is lower. Does everybody understand those two relationships? Any questions about that? here's some different materials. And last semester, I think I got a lot of questions about what's the equivalent sand roughness of stainless steel, because that wasn't in the textbook, and that's something that you had to know for the lab. And so we said, well, it's probably a little bit more smooth than cast iron. You could use steel and maybe even take it down a little bit from there, because that stainless steel in the lab is a pretty nicely polished steel. Here's some other materials, and they're equivalent roughnesses. You see that glass or a drawn tubing like copper or brass considered very, very smooth. And these are all listed in millimeters and both the equivalent roughness in feet. Really commonly to have galvanized pipes or wrought iron pipes. You can see that they're relatively smooth. But then some of these have really high equivalent roughnesses. For example, concrete pipes aren't very efficient for carrying pressurized fluid, both because the fluid will seep out of the seams where the concrete pipes join together, but also because they have such high roughness that there's a lot of energy loss through a concrete conduit. Corrugated metal, corrugated being, a corrugated sheet is looking like this. Why do they corrugate sheets like that? Do you know?
For strength.
Yeah, it's for strength. It's going to be a lot more rigid to do that than like this. Or you could just have the same very thin piece of metal. If you make a pipe out of it, it'll be very easy to crush. But if it's corrugated, then it gives it additional strength. And so our corrugated metal pipe, let's see, the corrugations are in the direction of flow, actually. And so when the water is flowing over it, those corrugations are very, very big, and there might be tiny little roughness elements associated with the material itself, but it's the corrugations that can add a considerable amount of equivalent roughness to it. So here's a wood pipe. We don't have any wood pipes in Huntington that I'm aware of, but we do have some pretty old-timey pipes in town. We've got some brick-lined channels that are carrying stormwater and sewage. But there are still some communities in the U.S. where they've got these wood-lined pipes, and usually it's because they don't know where they are, or it's a pipe that doesn't really carry flow anymore, but it still may be connected to the network.
What was the point of that?
Of a wood pipe?
Like, what was the advantage? Cheap?
The advantage was, I guess, cheap, available materials, and it's when steel was a lot more expensive than it is now. And reinforced concrete didn't become a common building material until about the turn of the century. So this would have been maybe like 1800s, where metal was very expensive, and it really wouldn't have been practical to put in a metal pipe all the way from a treatment plant to someone's house. And certain lines may have been just wood. So how thick is that laminar sublayer? That is the question that's addressed by the Morris and Wiggert criteria. Morris and Wiggert say that you can estimate the thickness of the boundary layer by considering the kinematic viscosity of the fluid and the shear velocity. So they say that you can estimate it as 11.6 times the kinematic viscosity divided by the shear velocity. And then that will give you the length in meters if you used SI units and all of those variables. Okay, and again, to use the shear velocity, then that is the shear stress divided by the density of the fluid. So here's a little diagram here that shows some roughness elements, and here's a velocity profile, and above the laminar sublayer, conditions are turbulent. And in this particular case, it looks like the roughness elements are fully submerged in the laminar zone. So for it to be considered hydraulically smooth, the surface, then what we want is the laminar sublayer to be at least 1.7 times the thickness of the roughness elements. So If it's hydraulically smooth, those conditions are corresponding to the diagram we looked at previously in the diagram that shows F values, the Moody diagram. It's the transitional zone. So to the left of that dashed line is where conditions are hydraulically smooth. You see it even says smooth pipes. So roughly speaking, we can calculate whether a pipe is hydraulically smooth or hydraulically rough. So if the thickness of the boundary layer is less than 0.08 times the elements, then that's hydraulically rough. That leaves a huge no man's land there between 1.7 and 0.08 times the equivalent roughness. But at least we know greater than and less than some sort of a boundary line. And so what you see, for it to be hydraulically rough, what that means is that the laminar zone is much, much smaller than these roughness elements. And so the roughness elements are projecting into the turbulent zone. And remember, once we get into the fully turbulent flow, what that meant was that the F value wasn't changing with increasing velocity. The F value was only a function of the relative roughness. So that was the point of the Moody diagram where the F values were flat. That was hydraulically rough, whereas hydraulically smooth is where the F value was dependent on the Reynolds number. And so further increasing or decreasing the flow through the channel does affect the F value if the laminar zone is much thicker than the roughness elements. So let's consider those principles in the context of this example. We've got a tank that's feeding water into a building. We know the flow rate that's required and the pressure that we've got to have. The length of the pipe, the diameter is known, and the friction loss is already known. And so what I'd like you to calculate is the water surface elevation that's required in the tank using the energy equation, which is provided here. And so once you know what water surface elevation is required to make this all work, then you can find the friction factor. Originally, the friction loss is already known, 16.4 meters. So then in this second bullet point here, to find the friction factor F, you're going to be substituting in that known friction loss into the Darcy-Weisbach friction factor equation, finding F. And then finally, once you've done that, together we're going to go through and apply the Morris and Wiggert criteria to try and find the thickness of the boundary layer, and then find out, in this case, is it hydraulically rough, hydraulically smooth, and so on. So go ahead and on your own calculate the water surface elevation needed in the tank, and then also the F value that's resulting in this situation. So we can break up the energy needed in the tank. The tank has to be a certain height to get over some of the obstacles to flow. First of all, it has to be at least as high as the top of the building. So that Z2 is the 20 meters. It's got to be at least that. Plus, we have to give it some additional height to pressurize the pipe. So to get it up to 350 kPa, we have to elevate that tank an additional 35.678 meters. Then we've got to elevate it a little bit more to give it velocity head. So velocity head's relatively minor, just 0.846 meters is what corresponds to the velocity head. And then finally, we've got to give it another 16.4 meters of elevation to deal with the energy losses due to pipe friction. So the final elevation of the water surface inside of the tank should be 72.9 meters. It's a lot less of a mystery when you look at an elevated water tank and you think, well, why is it that high? Well, they've got to have it at a certain elevation to just pressurize the pipe at all of the places in the network that they're serving. And so if you find out where that water tank is connected to, who are the people that are having their water pressurized from that tank? maybe they're a mile away. So you figure how much energy loss would there be in a mile of pipe, plus what pressure do you want there to be in those people's homes, what's the house elevation, and you can pretty easily sort of figure out why a water tank is the elevation that it is, and what sort of pressure it can be potentially delivering. Okay, so that solves the first thing. What's the water surface elevation? Of course, to find the friction factor, then we just rearrange the Darcy-Weisbach equation to h sub f d2g divided by lv squared. So 16.4 meters of head loss is known. The diameter of the pipe, 0.25 meters. 2g, 9.81 meters per second squared. The length of the pipeline here is 250 meters. And then the velocity, 4.074 meters per second, squaring that. So the F value is 0.0194. That's the friction factor. Now, this last part of the thickness of the boundary layer, we can calculate that because, first of all, we'll find the slope of the energy grade line, and that's h sub f divided by L. The h sub f is given as 16.4 meters of energy lost due to pipe friction over 250 meters of pipeline. So the slope of the energy grade line is 0.0656. Okay? The shear stress is known to be gamma hydraulic radius times the slope of the energy grade line. Okay, so that is 9810 newtons per meter cubed for the unit weight. A hydraulic radius is d divided by 4. Over there we found it was 0.0625 meters. And the slope of the energy grade line, 0.0656. Oh, and that's unitless. Meters per meters is unitless. So the shear stress, 40.221 newtons per meter squared. It's the shear stress at the interface between the liquid and the conduit. With that, we can find the shear velocity, V star. It's equal to the square root of shear stress divided by density. So that is the square root of 40.221 newtons per square meter, and the density of water, 1,000 kilograms per cubic meter, to the 1/2 power, 0.200 meters per second is the shear velocity. There really isn't any physical interpretation of the shear velocity, at least not that I understand. 0.2 meters per second, I don't really know that that means anything physical. Other than it allows us to calculate the thickness of the boundary layer in this regression equation. The Morris and Wiggert criteria, they say that you can estimate the boundary of the laminar sublayer by knowing the kinematic viscosity of the fluid. So 11.6 times kinematic viscosity of water, 1 times 10 to the minus 6 meters second per squared, meters squared per second, divided by the 0.200 meters per second. So if we look at the units of that, we're just going to have units of meters when we solve it. And it's 5.8 times 10 to the minus 5th meters. In other words, that is 0.058 millimeters. That's pretty small. That's the thickness of the laminar layer. So if we had some sort of a pipe, I'm going to exaggerate the roughness elements. Okay, so here's the pipe. What we know is that the laminar layer is 0.058 millimeters. That's how far from the edge of the pipe it is into the laminar layer. So let's compare that to some of the material types. Okay. Pretty common, cast iron. So cast iron is 0.26 millimeters. So for epsilon of 0.26 millimeters, what we said is for it to be considered hydraulically smooth, this layer has to be 1.7 times thicker than the roughness element. And in this case, the roughness element is already bigger than the laminar sublayer. So it's definitely not hydraulically smooth, but I don't think that we're necessarily going to make it into the criteria of hydraulically rough. What is 0.08 times 0.26? 0.08 times 0.26 millimeters. Can someone do that calculation?
0.0208.
0.0208. So for it to be hydraulically rough, then the boundary layer, this is our boundary layer, distance here is this. We have to be less than that, and we're not. So we're sort of in this no man's land. We're not strictly hydraulically rough, but we're not hydraulically smooth either. And the illustration of that we can see when we go to the Moody diagram. I calculated the Reynolds number under these conditions. The Reynolds number for these conditions is about 1 times 10 to the 6th. And we know that the F value, which we just calculated, was 0.019. So we're about here for our 0.19. So that's about here, right? So if we're about here, and then we go down to the 10 to the 6th,
Just on the other side, great.
it's right here. So it's still got a little bit of curve to it. You can see it's not yet perfectly flat. And so maybe that's what they mean by the this transition zone, is we're not hydraulically smooth, we're not hydraulically rough. Hydraulically rough is when it's really flat. Hydraulically smooth is when it's changing considerably as a function of additional Reynolds number, velocity changing. But where it's not changing a lot, but it's not yet fully settled down, I think that's the zone that we're in, because the laminar layer is pretty small. But the laminar layer is not so small that it doesn't have any influence anymore. So that just sort of takes the Morrison-Wiggert criteria to its conclusion, comparing how fully submerged are these roughness elements to the resulting F value that we get in an application like this. All right, so with that, I will see you next on Monday the 28th. So yeah, you've got a little bit of a vacation. And don't forget to watch those videos. I'll send out an email with the link when they're available. I'll also post the link on MU Online, so you'll have multiple ways to know what that is. And I'll see you then.